Hello all, welcome back to Data Science Brain. In this video, we will be doing another project where we will be making a recommendation system using Huggingface transformers. So let me just show you a quick example of what we will be making. So imagine a system to which we can ask something like, I want to watch a horror movie or I want to watch a comedy movie with my friends. And imagine that system will respond with the movies in the genre comedy. Okay, so comedy movie. Okay, like okay, let's say funny movie with my friends, and when I run it, it will return me movies that are in the genre comedy, and that has this description like happy comedy movie, science fiction movie. Okay, so this is perfect movie suggestion list to watch with my friends that lands in the genre of comedy. Okay, isn't it? Science fiction movie that has comedy in it. That's perfect for watching with friends, isn't it? So similarly, if I ask here like horror movie, horror movie, and system will respond me with horror movies. Okay, horror, mystery, psychological, science fiction movies. Okay, so this is perfect, isn't it? So this is a system to which we can ask questions like we can just say things. Okay, right? I mean, unlike the other recommendation system wherein we will be we'll be getting recommendations based on our past based on the movies that we have watched in the past. Okay, so this is like this is more like filtering using machine learning rather than recommendation system. Okay, so yeah, so that is what we will be building. So this will be purely based on NLP, natural language processing, using transformers library. And yeah, so let's get into the coding. Okay, so before we start, please take a moment to like this video, share this video with your friends, and subscribe to my YouTube channel if you haven't already for more such machine learning projects. So before we start coding, let me just give a quick shout out to this wonderful article by from KD Nuggets, from where I got this project. So I'll be leaving the link to this in the description. You can read through it. So let's start coding. So just like in any other project, the first step is to import the datasets, isn't it? So let us just use the usual library that we will be using, pandas SPD. And for the dataset, we'll get it from the this Kaggle dataset, anim recommendation database. So download this dataset and you can upload it into your Google Drive. And if you watched my previous tutorials, you know how to mount a Google Drive to your Colab project, isn't it? So just click here, mount to drive, and connect to Google Drive. So it will just mount your Google Drive here. So basically, this will allow us to use any files that are in our personal Google Drive folders. Okay, so it will take some time, and it has mounted the Google Drive here. So I will just go to my location where I have put this dataset, basically in learning and projects, Hugging Face, recommendation system, anim.csv. Okay, so I'll just copy the path to it, and we'll be using this path to load this dataset. Okay, so as usual, pd dot read csv, to it we will pass in the path, so it will read the dataset. This is just normal thing you have done many times. And let us just see the dataset. So it has anime id, anime id, and name, genre, type, episodes, rating, members. Okay, I think it's pronounced as anime, right? I mean anime, it's not anime, it's anime, right? And writing, members, everything. So so what we will be doing is, so we have the name of the anime, right? We have this genre, which will be probably the most important one, genre and name. Okay, so these are the textual data, isn't it? So these are the things that we will be using. So whenever we search for a movie, like when I say I want to watch a horror movie today, so what is that? It is a horror movie, isn't it? So I am looking for a horror movie. So in which column of this dataset should I look for if I want to watch if I want to watch a horror movie? I should look for the genre, right? So genre is the column where the type of the movie will be specified, isn't it? So similarly, in some cases, the movie names might suggest the type of the movie that it will be, isn't it? So these are the two things that will decide the type of the movie, isn't it? So the first movie, it's a drama, romantic, supernatural movie, so a guy who is searching for a romantic movie, will get this suggestion, isn't it? Should get this suggestion, isn't it? Romantic drama movie. He or she should get this suggestion, isn't it? And also maybe he want to watch that movie with his friends. Then this has a school movie, as a school as a genre, isn't it? So this should get suggested. So this is one important column for us, which we will be using to build our recommendation system, isn't it? So let us create a unique okay, before all of these things, we need to see the information of the dataset, isn't it? So we will say info, because we want to know if there is any missing values, right? So as you can see, there are a total of 12,294 entries, and as you can see, in the generate column there are missing values. So this is an important column for us. This is the actually probably the only column that we will be using for the using for training. Making the model. Okay, so we are not going to. We don't want to miss any data here. Okay, so for the purpose of this project, I'll be just dropping it. So there are many ways to handle missing data. For this project, it's a simple project. I will be just dropping these null values. Okay, so we'll be using the drop na function, and we will just drop the null values. So after I have done that, let us again just check the info to see if there is any null values left. Of course, I am stupid enough to just do that. So we should, it will return the dropped, return a data frame with the dropped columns. Okay, so we should save it back to the df. And now let us check this, and we can see it has dropped all the entries that were null. Okay, so that's the first thing to do. Now the second thing, as we have discussed, the important things that we need for recommendation system is the genre and name. So we'll combine these two things, isn't it? So in most cases, like in a movie name and its genre, it combined can, or at least give us a little bit amount of the description of that movie. Okay, in most cases. Okay, at least in some cases, the movie name and its genre together. If a person reads the movie name and the genre together, he or she can understand a little bit about the movie. Okay, so we can call these two columns together as the description of the movie. Okay, so we can create a new column named description, which will be a combination of name. Uh, okay, it has definitely given me suggestions. Okay, so this is one of the cool new features of Google Colab. Okay, it uses its AI to give us suggestions of what we should include, and that is perfectly good. Okay, so we need all of these things actually. We don't have any members or anything. We have the rating, right? Yeah, we don't need the members. It's just pure numbers. It doesn't represent anything. We can actually use the rating. Okay, so maybe I can say, like, I want a romantic movie with the rating of 9.4. In that case, maybe just I do want to use this. Or maybe I want to do one more thing. I want to just put a plus here. I want to say rating, and then I want this rating. Okay, so that is perfectly good. And episodes, this too, there's no meaning in putting it just like this, right? So I will say episodes, and then I will attach episodes to it, because in some cases, I want to ask that horror TV series with 5 episodes or something like that. Okay, and type, yeah. Okay, so we'll combine the name, generate, type, episodes, rating, and all for the anime movies. And we will make a description, okay, using all these columns. Okay, so these all columns can describe this movie, right? So now and see. So shift enter, and it will run. Okay, we have got an error here. Can only concatenate. Okay, of course. So here we have some floating point numbers or integers. Okay, so it cannot concatenate directly with this string. So we need to do something like this for the episodes, and for the rating. I think that should solve it. Yeah. So now let us print the df and see it again. we will have a column called description, and there it will be a combined text of genre, type, name, episodes, and rating. Okay, so now we have something to compare, isn't it? So we have the description of the movie. So our idea is to compare this description with whatever text we will give the machine. Okay, so we will be saying like, I need a horror movie to watch. So we will compare that sentence, horror movie, with the description of all these movies. Okay, and we will see if there is any matching description for horror movies. So that's how we will find the, and we will get the recommendations. Okay, so we'll match our sentence that we have given the system, or our question that we have given the system. Like, I want to watch a horror movie. We'll compare that sentence with the descriptions of these movies. Okay, so any movie that has a matching description to horror movies, or I mean, whatever question we have given, whatever query we have given, that will be, those movies will be that movies we need to recommend. Okay, so how are we going to do it? How are we going to compare these sentences? So for that, we will be converting these sentences into embeddings. Okay, so we will be converting these descriptions into embeddings, and also we will do the same for the sentence that we will be giving, and we will be comparing these embeddings. Okay, so what is an embedding? So embedding is, I will simply explain it. Okay, okay, so first of all, let us take two sentences. Okay, so we will say horror movies. So this will be our query. This will be what we will be sending. So imagine that this will be what we will be sending them. Okay, and okay, I hope you can see it. And another sentence, something like, a description. Okay, a description where the movie's description was like crime, horror, thriller, something like that. Okay, something like this. Okay, um, okay, so imagine these were the two sentences. Okay, so what we will be doing is, we'll be converting both of them into embeddings. Okay, so how will this embeddings look like? So embeddings are basically vectors. Okay, so there will be vectors of numbers. A vector is just like an array, so it will be having numbers like, maybe 2 point, this, one, maybe 0 point, da, 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 dot, dot, dot. And there will be so many values here. So this one vector will be representing a vector. I mean, this one array will be representing a vector in a really high dimensional space. Okay, if there are two values, that means, if there were two values, what does this means? What is this code, this vector means? Okay, I mean, what does this mean? This means a point in 2D space, isn't it? So this is basically a point in 2D space. So similarly, our this both these sentences will be converted to embeddings that represents vectors. Okay, so for the sake of explaining this thing, let us imagine that. Okay, I'll draw a line. It's been long since I have used MS Paint, so I am not quite sure how to do lines and everything. Anyway, okay, turned out pretty well. Okay, and so for the sake of explaining things, let us just imagine that a vector, that I mean, our sentences are converted to these vectors. Okay, it is not the case. It will be converted to a vector in a really high dimensional space, but we are doing it in a 2D space here. Okay, so imagine this is the vector, this is the embedding. Okay, so this is how our sentence will be converted. Our sentence will be converted to an embedding. Embedding is basically a vector. A vector has a direction and a magnitude, isn't it? As we have learned in mathematics classes in our primary school, maybe not primary school, and I mean in higher secondary school or something like that, we have learned that a vector has a direction and a magnitude, isn't it? So imagine our horror movie sentence is converted to this vector, and the description, the movie description, this thing is converted to a embedding, whose embedding, which is a vector that looks like this. Okay, so in this case, these two vectors, if we take the distance between these two vectors, it is really small, isn't it? So what does that mean? That means these two vectors are close. And what does that mean? That means the embeddings are close, embeddings are similar. That means the sentences are similar. Okay, so that's how we will be finding the similarity measures. We will be converting each of these descriptions into embeddings, basically vectors, and we will find the embedding for the input sentence, and we will convert that vector, we will convert that vector to all the vectors of the embeddings, I mean all the vectors of the descriptions of the movies, and we will see which two, I mean which all vectors are similar, are have very small distance between them. Okay, and we will list all those sentences. Okay, we will be returning two or three of the first, maybe first three or first five sentences whose vectors are close. Okay, so whose vectors are close. Vectors are close means sentences are similar, isn't it? So I will repeat again. We will be converting each of these sentences into embeddings. Embeddings basically means vectors, vectors of numbers. Okay, vectors of numbers representing represented in a higher dimensional space. Okay, for the sake of simplicity, for explaining, I have drawn these two sentences as vectors in a 2D space, and these two vectors are close together. If you take a distance measure, these two are close together. So that's why we have concluded that these two sentences are similar. Okay, so similarly, we'll be taking cosine similarity for all the embeddings we'll be having. Okay, and we will see which all sentences are closer together. We will take the top 5 of them and we will return that. That's how we are going to work here. So that's how we will be doing it. So for that we need transformers. Okay, so that's the library that we'll be using, and we have some classes here in this library. I'll be just importing some of this. We'll also use Pytorch here, and for writing some functions. So we have auto tokenizer and auto models. These are the two classes that will be used for loading the loading the model and its particular tokenizer. Okay, so these both, I mean the machine learning model that we'll be using is a natural language processing model. Okay, it's called a sentence transformer. So I'll just load the tokenizer and also the model as well. So if you have learned NLP, you must be able to understand this, what is a tokenizer and everything. So we will be, I mean most of the NLP models require the sentences to be converted into a tokenizer before it gets processed in the by the model. Okay, so I mean most of the models require the natural language processing data, which is in this case our sentence, to be converted into tokens. Okay, so we need it to be tokenized before we can pass it to the model. Okay, and there is a requirement that we need to use the particular tokenizer that the model itself has been used for its training purpose. Okay, so whatever tokenizer the model has used for training, we need to use the same tokenizer for tokenizing our sentence. Okay, so we are actually not training any model here. Okay, so we are just using the model, we are just inferring from the model. Okay, so that's why we have to use the same tokenizer. So let us just quickly look at this model actually to better understand what it does. So sentence transformers is the model that we'll be using. Okay, so sentence transformer model, it maps sentences and paragraphs to a 384 dimensional dense vector space. Okay, just like I have said, it basically just transforms a sentence into a vector. That's all you have to understand here. Okay, you can further look into it. I will be providing the link to this in the description, or you can just search it. So that's all it does. It will convert a sentence into a vector. Okay, and two vectors, if they are similar, basically if both of them occur in a smaller distance in that space, then that means those sentences are similar. Okay, so that's all you have to care about here. So now let us just try out if this thing works. What will we get the output as? So for that, let us give sentences, some great movie. So these are two sentences that we have. So just tokenize this and see the output. Okay, so I'll just copy the code that I have written already to save some time. So we will say encoded input is equal to tokenizer. We will use a tokenizer. So as I have mentioned, we need to convert the sentence into tokens before we can pass it to the model. So we'll say tokenizer, we'll pass into it sentences. We'll set the padding and truncation to true, and the result will be returned as tenses. Okay, so PT here stands for Pytorch tenses. Okay, so we are using Pytorch here for writing some functions. So we need to return it as Pytorch tenses. Okay, tenses. Okay, and we have set the padding to true because this will ensure that the all the sentences in one batch will have the same length by padding them to the length of the longest sentence in the batch. Okay, so this is important because most models generally expect input of uniform size. Okay, and without padding, sentences of different lengths would cause issues during the batch processing. Okay, so that's why we are setting padding to true, just to make sure that all sentences will be having same length. Okay, so if sentences that has length smaller than the largest sentence, we will just add a padding to it. Padding means we'll just add some bits to it. Okay, that's all. And we have given truncation to true. So this will ensure that any sentence longer than the model's maximum allowed length is truncated to fit within this limit. Okay, so there will be a maximum allowed length for a particular sentence to get processed, okay, at a time. So if the sentence goes beyond that limit, it will just truncate it. Okay, so it will just remove the last few words. Okay, so truncation is important because most model will have a fixed maximum input length. So example like 512 tokens for BERT model. Okay, BERT is a one of the famous models, transformer models. So it has a token length. Not token length. Maximum input length of 512 tokens. Okay, so these sentences will be divided into converted into tokens, isn't it? So there will be a maximum length for a number of particular tokens that is that the model can take. So that's why truncation is set to true. So that's let us just run it and let us see how the encoding looks like. So as you can see, our tokenizer has tokenized this sentence into tokens. Okay, so these two sentences are converted into bunch of numbers that are called as tokens. Okay, the first sentence has numbers like 101, 2070, 2307, etc. And the second sentence also has some array of numbers. Okay, so that is what tokenization does. Okay, so it will convert sentences into tokens. Okay, basically some kind of numbers that is machine understandable. Okay, so that's the first thing. After tokenization, we can pass these encoded sentences into our model. Okay, so now we can use our model. So again, as usual, I will just copy and paste the written code and explain it. Okay, so we are saying with torch dot no grad. So no grade means we are not going to find any gradients here. So why do we need gradients? We need gradients. If you have learned machine learning, we are using gradients for learning purpose, isn't it? So like gradient descent algorithm, it will try to find the optimal model, isn't it? So we are not finding any gradients here because we are not training anything. We are just inferring. We just need the model to take our input and give us some output. Okay, so we are using a pre-trained model and we are just inferring from this pre-trained model, so we don't need to find any gradients here. So to the model, we are passing in the encoded input, and we will be expecting some model output here. Okay, and this 2 stars here, this is just used for unpacking in Python. Okay, so like our input here is given as tensors. So this is a dictionary that contains the encoded input data, okay, with keys corresponding to the expected input names. So we are just unpacking that. Okay, so let us run this and see the model output. So as you can see, as I have mentioned before, it has converted these sentences which we have tokenized into bunch of embeddings. Okay, so it has converted into vectors. Okay, so each tokens into a vector. So that's what it has done. So that's the output. It's a long output. You might not understand anything by reading it. So that's actually half of it. Okay, we have actually converted all the descriptions into, not all the description, our example description into example sentences into embeddings. Okay, so now after we have done that, we need to do few more things. Okay, so we have one problem here. So we have successfully converted all the tokens that we have passed into our model into embeddings, but in here each array, each embedding, each vector, this is a vector. Okay, so an array of numbers, it's a vector, isn't it? So each vector represents one token only. Okay, so we have basically converted each tokens into embeddings, but what was the requirement? What did we need? We need each sentence as a vector, isn't it? We need the whole sentence to be to be converted into an embedding, isn't it? Not just single tokens, isn't it? So for that, we need to sum up these token values and take the average. Okay, so to sum up these embedding values for all the tokens and then take the average to get get one vector, one full vector for this particular sentence. Okay, so what are we going to do? We need to, I mean, this is embedding for one token only. So we'll sum up this for the number of tokens for that particular sentence. So we'll take the sum and divide by the number of valid tokens. Okay, so I am going to just going to imagine that this is 1 2 3 4 5. So there are 5 tokens converted into embeddings here. So I guess there were 5 tokens here as well, isn't it? 1 2 3 4 5. So there were 5 tokens. So these 5 tokens are converted to 5 embeddings here. Okay, so 5 vectors. So we are going to take sum of these 5 vectors. Okay, we are going to add these 5 vectors, and we will divide it by the number of tokens. Okay, number of valid tokens. So here we have 5 valid tokens, isn't it? So there are valid like valid tokens and invalid tokens. So why is there? Because we have added this padding equal to true and truncation equal to true, isn't it? So I mean, not truncation, padding equal to true. We have set padding equal to true. Why? Because we need equal number of equal length for tokens, isn't it? Because otherwise the model won't be able to infer anything, because the models require that for a particular batch all the sentences will be having same length. So that's the reason why we have added padding. So if at all one sentence doesn't have a valid token, it will be represented as 0 here. Okay, so basically if there was no word, there were no word to convert to token, so it has just added a padding. So I will show you how it will look like. Okay, so let me just uh, copy one of those. Okay, why is it not scrolling up? Okay, so let me just copy this. So imagine the scenario where this was the tokens for this particular sentence, the first sentence, some great movie. Okay, copy and paste this here. Okay, and imagine another funny movie. There was another word. Okay, there was one more word for another funny movie, and something like movie I watched, and this had more tokens. Okay, this had more tokens like this. Maybe in that case the length for this vector and this vector, this token vectors, is different, isn't it? So we need to match this length. So what will our tokenizer do? It will add a padding. Okay, it will add these paddings to it. Okay, it might not look exactly like this, but basically it will just pad it to make it the same length. It will just add some like some particular tokens that are paddings. Okay, that are not actual conversion of the words. It is just padding to make sure that both the lengths are equal. Okay, so that's the case. So in that case we will get an id for each of these tokens. Okay, like attention mask, it is called as attention mask. So if the attention mask has all one, it means that all of them are valid tokens. So in this case our attention mask will look like this. I'll show you. So our attention mask will look like 1111 5 ones and then 2 zeros. Okay, so that's how it will look like. So coming back to what we were talking, so we need to, what we need to do, we need to sum it up these 5 vectors and divide by the number of valid tokens. Okay, so that's what we are going to do. So I'll write a function for that. I have a predefined function for that. I will write it down and then I will explain to you. Okay, so this is the function that we'll be using for doing that. It's called mean pooling. Okay, so basically mean, I have said that I'll be taking the average, isn't it? So that's why mean pooling means just aggregating. Okay, just aggregating. So that's exactly what we are doing, isn't it? We are aggregating and then finding the mean. We are adding the sum, we are summing this up. So this, what does this represent? This represents the vectors for all the tokens for one sentence, isn't it? So this represents that. So we will be summing this up and then what, we'll be taking the average. Okay, so that's what we are going to do. And we have similarly we have the token embeddings for the second sentence as well here, isn't it? So yeah, so that's what we will be doing here. We will sum it up and divide it by the total number of valid tokens. Okay, so let us do that. So that's what this function will allow us to do. So I am having an error here. Okay. So we need to pass in the model output and attention mask. I have printed it out and shown you before, I believe. Attention mask. So attention mask is part of the encoded input, isn't it? And we need model output, which is this one. Okay, model output here. So we'll pass in these two things to this, and we will be receiving the mean pooled. Uh, Basically, let's say sentence embedding. Okay, sentence embedding. Yeah, exactly. So basically, what we had was token embeddings, isn't it? So we need to convert that to sentence embedding by doing mean pooling. So for that, we will pass in encoded output and model output and attention mask. Attention mask we received from the where from the encoded input. Okay, this one. So why do we need the attention mask? Like I mentioned before, it will be having padding, isn't it? So if it has padding, that's not a valid token. So for knowing that, we need attention mask. Okay, only then we can divide it by the total number of valid tokens. So let us run this and see the output. Okay, we will run this first and then this. So yeah, as you can see, it has converted this one full vector. Okay, this one full vector represents one sentence. Okay, and the next one vector represents the next sentence. So it has successfully summed up all the token vectors and made it into one sentence embedding vector. Okay, so that's what it has done. So a quick explanation for whatever is happening here. So basically, we are taking the token embeddings from the model output. Okay, so the first element of the model output contains all the token embeddings, as you can see here. You can just go through this array and you can understand that. And yeah, and then we will expand the input mask. Okay, so why do we need to expand it? So what is expanding doing? Okay, I will just show you an example to make you understand that. So imagine our attention mask looks like this. Okay, so it's a tensor. So it has 111 and 2 zeros. Okay, so 2 were not valid tokens. Okay, just padding. So imagine this is the tensor. This is the attention mask that we have. So what will the first thing do? Unsqueeze. What will that do? So after unsqueeze, this is how the uh, this is how our tensor will look like. Okay, so okay, oh, I have just run it. Oh no. Okay, it's fine. I will just run it again. And okay, so this is how our attention mask will look like after that. So we have basically converted, we have basically taken all these elements and made it into a single value. Okay, single 1D value. Okay, so before it was a 1D tensor with a shape of 5. Now it is a 2D tensor. Okay, with a shape of 5 comma 1. Okay, so that's what it does. So why do we need to do it? So basically, okay, I will explain one more step and then I will explain. Okay, so then we will expand it. Okay, then we will expand it to the size of token embeddings. So imagine that our token embeddings had a size of maybe something like 5 comma 768. Okay, so it means that there is 5 is the number of tokens and the 768 is the dimensionality of each embedding. Basically, what is dimensionality? What does that mean? Basically, the numbers that you have seen there. Oh, why is it not going up? Okay, basically this size of this one vector, that is 768. There are 768 numbers here. Okay, basically representing some kind of a point or something in a higher dimensionality space. Okay, so dimensions means basically numbers. This if it had two numbers, that is 2D. Okay, 2 dimension. Okay, so this has 7. Maybe imagine that this has 768 numbers there. That means 768 is the dimension. Okay, so so we need to convert our attention mask, which is a 1D tensor, into a 5 comma 768 dimension tensor. Okay, a 2D tensor. So that's why do we need to do that? Because that will enable us to do some of these operations, element wise operations, because both the attention mask and our token embeddings need to be in the same dimension in order to do some operations. Like you can see, we are multiplying it. This is element wise multiplication. For that, both of them need to be in the same dimension. Our token embeddings will be having dimension which is similar to this. So there are 5 sentences, and for each 5 sentences there are 768 embeddings. So our input mask expanded. Basically, our attention mask also need to be in the same dimension. So that's all the reason why we are expanding it. Okay. So and squeeze will basically like take all these values from inside this 1D tensor, and it will convert all of them into a 1D tensor itself. So it will in total it will make it to a 2D tensor. Okay. So that after doing that, we will be expanding it into a size of our token embeddings. So that will make it into the same size of our token embeddings. Okay. So that's all what we are doing here. And just just for clarification, why are we doing to float? Okay, because dot float will be enabling us to uh, do these multiplications easily, because our embeddings will be floating point values. Okay, but our attention masks aren't, they are basically integers. So basically, to convert into a similar format, we are doing this to float. Okay. So I hope you understood what I have just said there. If I said it quickly, you can ask it in the comments. I will be happy to explain it again. Okay. So that's what we are doing it here, by expanding the attention mask. Okay. Basically making it into a same dimension of our token embedding so that we can multiply it. That's all. And after that, as we have mentioned before, we are summing it up. Okay. So we will be multiplying token embeddings. Why do we need to multiply again? As I have mentioned before, there are paddings, isn't it? There are invalid tokens. So we don't need that. So by multiplying, we will be removing those invalid token embeddings. Okay. So after expanding, what happened? We have received the same dimension. We have received tensor with the same dimension as the token embeddings, isn't it? So it has zeros here. So whatever tokens that was in that were invalid, all of its embeddings will be multiplied with 0, and the output will be 0. Okay, basically making the invalid tokens embeddings 0. That's all. Okay. And we will sum it up here, torch dot sum, we will sum it up here, and we will divide it by the mean, isn't it? So that's what we are doing here. So we are taking the sum of input mask expanded. So that will be the total number of valid tokens. And we have set here min is equal to this value. Why? Because we don't need to divide by 0, isn't it? We don't have to divide by 0. That's why we are doing a clamp here. We are basically saying that if the sum is 0, then clamp it to this value. Okay, we don't need to get a divide by 0, which is an error. Okay, we cannot divide by 0. So if it comes 0, then the minimum value should be this. Okay. So that's what we are doing by taking a clamp here. So we are dividing the sum by the mean. Well, I mean total value. We are dividing the sum by total valid tokens, and it will return us the sentence embeddings. Okay, and we have received it here. So that's how that function works. Basically, we have received the sentence embeddings from the token embeddings. Okay, we have summed it up and divided by the total number of valid tokens. So now that our example works fine, our example sentences have been converted into sentence embeddings after getting converted into token embeddings. So we can now proceed with our own dataset, isn't it? So before that, I will tell you one thing. We actually don't have to do it like this. Okay, we don't have to write these many codes. Actually, Huggingface has a library. Okay, Huggingface has a library, that will enable us to do this in just 2-3 lines. Okay, so you need to install this pip install sentence transformers, and we will get our model from this library. Okay, so if you do that, we don't have to go through this all these lines of code to transform our sentence into sentence embeddings. Okay, we can just say model is equal to from sentence transformers, we can get the same model from here, and then we can say our anim embeddings is equal to model dot encode, and we will pass in our description. Okay. So we needed to get our description into sentence embeddings, isn't it? Only then we can compare it into the embeddings of our input. So we will pass in the description column of our data frame into sentence transformer. Okay, I mean sentence embedding. Okay. Okay, I haven't imported that. So this will do whatever we have done in just one sentence. Okay, one line of code. So we have imported sentence transformer, and we have we got the model from sentence transformer library, and we will be passing in our description to our model. We are saying model.encode. Okay, so this will do all the things that we have done before. Okay, so after that we can just print it just to confirm this is doing exactly what we have done. It will take some time. So it has finished running. I'll just run this and show you. As you can see, just like before, it has converted our sentences into embeddings. Okay. So I mean, our anime embeddings had so many sentences. That's why we have so many vectors here. So each vector represents one sentence here. Okay. So we have successfully converted our descriptions into sentence embeddings. Now what do we need to do? Now we can pass in a query, isn't it? So we can say a query is equal to, we can test it, isn't it? So let's say, say horror movie to watch. Okay. So now after this, what do we need to do? We have to embed it, isn't it? So we have to embed it, and then we have to compare it with uh, our anime embeddings to find out if it has a similar embedding, isn't it? So let us write a function for that. We'll write def get recommendations. I'm getting suggestions, okay, because as I have mentioned, this is done from that KD Nuggets article. So some other people might have tried it out. So that's a really good feature from Google Colab. You will be getting recommendations, suggestions from Google, I mean from GitHub accounts. So we'll say query embedding is equal to model dot encode. Oh, it has given me the whole code. Okay, anyway. Okay, so this is what we'll be doing. Not exactly this. We'll be importing cosine similarity from scikit-learn library. Replace this with this, and we'll say similarities. Okay, so we will encode our sentence, and we will find the cosine similarity, basically the distance between one of the query embeddings, our query embedding, and one of these anime embeddings. Okay, so that's what we will be doing here. And now we will say top indices, because we don't need all of the similarities, isn't it? We just need the top similarities. That means the top the closest vectors. We only need the closest sentences, isn't it? We don't need all the sentences. This will return basically the similarity measures of all the sentences with our sentence. Okay, basically the distance of all the vectors with our vector. We don't need that. We only need the top maybe 3 or 4 or 5 of them. Okay, so that's what we need to do. Top indices is equal to underscore here. Top indices is equal to similarities dot, okay, it's not like this. So basically we are sorting it out and finding out just the top few of it. Okay, not top k, top, okay, top k, yeah. So basically we have said here we only need 5 recommendations. Okay, so if we needed more recommendations, we will pass in that number here. This will basically sort it and take the top 5 of it. Okay, that's all it is doing. This will return the similarity measures for our sentence with all these sentences. Okay, we only need the top 5. So that's what we are doing here. We are sorting it and taking the top 5. Okay, that's all, and we'll return that. Now we will run it. We'll say recommendations is equal to get embeddings. We'll pass in our query here and anime embeddings and also the data frame. Okay, now we will get the recommendations. We will print it out here, and let us see. Yes, as you can see, what was our query? We need horror movie to watch, and what we receive? We received movies in the genre of horror. Okay, horror, mystery, drama, adventure, horror, thriller. Okay, that's wonderful, isn't it? That's really good. Now, just to show you that it is, I'm not making you fool. I'll try it out with funny movie as well. Okay, I have run that and run this. This will basically take the embeddings of this sentence, and it will compare it with the embeddings, all these embeddings, and it will return us the top 5. Okay, so if you want, we can get the top 3 actually. Maybe some of you only need the top 3. So we'll say 3 here. Okay. So I have already done that. Okay. So we have received funny movies. Okay. So see, all the genre had comedy in it. Okay. So we have received top 3 funny movies from our movies list. Isn't that wonderful? So that's all about our project. It's a short project, I know. So I hope you like this short project. You can obviously, try out different things with this data set, and maybe make this better, and maybe do something differently. And if you have any doubts regarding any of these things that I have explained, kindly share it in the comments, and I'll be sharing the link to this code in my GitHub repo, and I'll be sharing that link in the description, and also the other resources links will be in the description. Okay. So that's all about it. I will see you in the next project.